Bismillahirrahmanirrahim. Assalamu alaikum students. So this lab is about advanced programming, and the objective is to understand the operation of shift registers, data movement, and arithmetic instructions. So there's some typing mistake over here. It should be arithmetic. So we'll be learning that how to use shift registers, what are they used for, and what's the basic aim of this lab. The shift register is a number of internal relays grouped together, normally 8, 16 or 32, which allows stored bits to be shifted from one relay to another. The grouping together of internal relays to form a shift register is done automatically by a PLC when the shift register function is selected. This is done by using the programming code against the internal relay number that is to be the first in the register array. So you don't need to be worried about it. I'll be showing an example of this to you guys. Shift registers can be used where a sequence of operations is required or to keep track of particular items in a production system. The shift register is most commonly used in conveyor systems, labeling or bottling applications. So these are the uses of shift registers, and now we'll move to the data movement instructions. There are typically two common instruction sets. The single instruction is commonly called the move. It copies a value from one address to another. The move instruction needs to know two things. You need to remember these things: source and the destination. So source is where the data we want to move is located, and destination is the location where we want the data to be moved to. We'll write an address here. So basically what's move doing is that move will move or copy our data from one address to another address. So the data can be moved to physical outputs as well. We'll see this in an example. The third thing that we are going to learn today are the arithmetic instructions. We are going to use the addition block, the subtraction block, the division block, the multiplication block, and the square root block. I'll be showing you these things in an example, and I'll be expecting you guys to do the whole task by yourself. So arithmetic instructions in a PLC include the basic four operations of addition, subtraction, multiplication, and division. In addition to these four math functions, large PLCs may also include square root operations. So in the addition block, an add block adds two values stored within the controller and places the sum in a specified register. So we want to add two values. We'll be using the addition block, and the addition would be in binary, but you can convert that to hexadecimal or decimal or BCD. The operand values can be fixed constants, values contained in input-output registers or holding registers, or variable numbers stored in any of the memory locations. Here's a figure that will be illustrating you guys about how is the register and this block working. So you can see that 973 has been stored in the register 1000, and 119 has been stored in the register 1001, and the result is being stored in the register 2000. This is the add block, and this will perform the addition when you have turned this control line on, and it will result in operation command, that is, if you are having two operands like 1 plus 2, it would not add these two numbers, that is, it would not give the result equal to 3 until this control line is on. Then as you can see, a control line enables the operation of an addition block. When the run conditions are true, the processor performs the addition function. In the blocks shown above, register 1000 and register 1001 can be preset values, storage registers, or input-output registers. You can mention any of the input addresses, fixed values, variable values, or memory values in the inputs over here. I'll show you guys how to use it. Each time an off to on transition enables the control line, that is, the toggle enables the control line. Instruction adds the values in these two registers and places the result in register 2000. Done or enable output coil indicates that the operation has been completed. this output remains on as long as the control line is true. Then is the subtraction block. It performs the function as it is in the similar way as the addition block, and the subtraction block will subtract this second operand from the first operand. So operand is basically the number that you are adding or subtracting. So register 1000 minus register 1001. The control input in this subtraction block operates the same way as in an addition block. When the rung condition, that is this control line condition, is 1, the controller will perform the block operation, and 3 registers hold the data. First 2 registers are going to hold the operands, and the third register 2000, is going to result the output. And the values that these registers can hold vary in format and may or may not include the sign bit. So we'll see in the example that whether it holds or not. Then is the multiplication block. The multiplication block function uses 2 registers to store the result. One register is to hold each of the operands, and a figure illustrates the multiplication block over here. You can see this figure over here. So the overflow would be stored in 2001, the output in 2000, and these values will be stored in one register. Then is the division block. They are all performing in the same way. They'll be picking up values from registers, or you can mention fixed values to these input blocks. Then is the division block. The division functional block finds the quotient of 2 numbers, storing the result in 1 or more registers. Here's the figure for this block. The division calculation begins after the control rung has continuity. You can see that this control line, whenever this will turn on or become true, only then this division block will perform the division and store the result in 2 contiguous destination registers. The destination registers would be 2000, which would be holding the integer part of the result, and register 2001, which holds the decimal fraction part. So depending on the controller, the second result register may hold the remainder instead of a decimal fraction. Some controllers also allow a scaling factor to be specified in a division block. This scaling factor, yes, this is something really important, that this scaling factor permits the fractional results which would otherwise be lost to be scaled and stored in a register. Here's the scaling factor. You can include it in your block. So the final block that we are going to use today or include in our lab is the square root block. The square root block instruction generally has 2 or 3 registers that hold the value to be operated on, and 1 or 2 other registers that hold the result of the square root operation. One of the registers may hold the integer part of the result, while the other holds the fractional part. And the processor may also provide scaling. Once the control rung has continuity, here's the control rung, it would be performing operation of the square root, and then the enable would show us that the square root operation has been completed, and the result would be stored in 2000 and 2001. Then we have the conversion blocks. This simply converts the source data to BCD and transfers to destination addresses that we want. So this is simply a data converting block. Now let's move to the tasks. The tasks include turn on 2 LEDs alternatively after 1 second using BSL bit shift left and BSR bit shift right. Then we have to implement logic using move and MVM. These are the tasks that you have to perform, that you have to turn the even LEDs on of the output 2, then the odd LEDs, and so on. And then you have to implement a 8-bit calculator which can perform the following functions: addition, subtraction, multiplication, division, square root, and negate. And then you have to use BCD simulator in this task, and input 1 should be I150 to I157, and input 2 should be I158 to input 1515. Let's move to the example that I need to perform for you guys. So here I have implemented added an add block in my system. a BSL block in my system and a move block in my system. What I need to show you guys over here is we'll start from the BSL, bit shift left. This is one of the move commands that moves our bits from one location to the other. This is the file instruction that I have mentioned to be N7 register, which is the integer register. You can choose any of the registers and you can see that this register would be moving values from one location to another. One more thing that you should notice over here, that I've mentioned the whole register over here. I've not mentioned any of specific 1, 2 or 3 values. Rather, I have mentioned the whole register N7 colon 0, whole row 0 of N7. Then we have control R60. You have nothing to do with this. It should be R6 colon 0 because this is the control address of each of these blocks in RSlogixpro. Then is the bit address. Bit address is the location of that bit that you need to move or shift left in this register. So I have mentioned it to be I1 colon /0. This means whenever I1 /0 this switch would be on, it would be shifting a bit 1 in this register, and whenever this would be off, this would be shifting a bit 0 in this register. And then I have chosen length to be 10 over here. This is basically the length of the word that we are, or the bit that we are going to shift, and I have chosen 10. You're already familiar with the length that we use, so I'll just download it to PLC and then I'll go online and select run. I'll just open the data table. You should not be focusing on this add block over here right now, but the BSL over here. So I'll go to the N7 integer register, and now what you would see is that first of all I'll turn this bit on, which is the bit address, because I want to shift a 1 in this register. So I'll be turning this one on, and you can see that after I turned it on, it has performed some operation and some of the lights over here have turned on, but just ignore it for now. Now what I'll do is that I'll turn on this I1 /1, and you can see that a 1 has appeared in this register from the and it will move to the left because it would start from N7 colon 0 /0, and now when I turn it off and turn it on again, it has moved a 1 again to this register, because the value that we have moved, or the bit address that we have moved, is at 1 state, at the true state. Well, what happens if we turn it off? And now you'll see that when I toggle it, turn it off and turn it back on, now a 0 has been appended in this register, and the rest of the bits have moved to the left side. So this is how this bit shift left works. You can see if I turn it off and on again, it has again shifted it left and appended a 0 in this register. Now if I turn it on, which is the bit address, and then if I toggle it, you can see a 1 has appeared again in this register. So N7 colon 0 register is being changed by the bit shift left command block. Now what we'll do is that we'll just close it off, we'll go offline, and then we'll clear the data table. Okay, now you can see that here's the add block, and what's the add block doing? That it would add the value from I3 colon 0, which is this one, to and the source B, which I have fixed to be 25. I have inputted a fixed value constant 25 over here, and the result would be stored or shown at the O2, which is this block, which is the basically LED rack over here. You can also mention any register over here. Here's the decimal value that's being shown over here, What I'll do is that now I'll go download it to PLC and I'll just go online after it, and then I'll turn this back to run command. You can see that I1/0 is the rung or the control command of this. It would not perform any addition until I have turned this input switch on. So basically what needs to be the answer right now is 25, because this is the constant 25, and I3:0, which is this input line, is all zeros. What if I turn one of them to 1? So you can see that after I've turned this one bulb to on state, here the I3:0 has turned to the position 1. What if I turn this to 15:1 to on? It is 32,768, because this is acting as 0 0 0 0 0 0 0 0 in the opposite direction, so it would be 1 0 0 0 0 up till 14 zeros ahead of this 15. So I'll just turn it back off and turn it on, and here's a 1 and here's a 25 in the constant source B. Now the destination is still 0, which is O2. What will happen when I turn this I1/0 on? It has performed the addition, which is 26, and according to this 26, it has turned the bulbs on in this O output 2 column, which is the output rack of these LED bulbs, and the bulbs are rightly in the sequence of 26. What if I turn this on? You can see that here it becomes 3, and the output is now 28, and the bulbs are turning on in the sequence of 28. Turning back on any of the lights, you can see that this is now 35, and which is being added to 25. The answer is 60, and the bulbs for the output value are being turned on. So the next block that we are going to use over here is the move block. So this is pretty simple. It uses the source N7:0 register, and I can change it to any other register, but I've chosen this one, N7:0, which is also being used over here, and this would shift its value to the destination output 4, that is this one. Okay, so what is the value of N7:0 right now? We should see that. Go to data table, and we'll change this to N7 integer, and you can see that N7:0 is all zeros right now. I'll change it to hexa BCD. I'll change this to FF, 4 Fs. Okay, so this means that it's all 1, all lights should be on, and now this value should be transferred to the output column 4, which is these bulbs. So when I'll turn this input switch 1/2 on, that you'll see it has turned all of these output lights to be on, because the instruction N7:0, which is FFFF, has been transferred or moved to the output destination 4. Now I'll show you that if I change this to 00FF again, I should turn this off first, and if I turn this to FF 0, I guess, okay, 1. So let's see what happens over here right now. If I turn this input 1/2 on, it has turned only one of the lights to be on. Here it is. Now if I change this value to 36, what happens is that when I'll turn this output input 1/2 on, it would turn these lights on in a way that it shows 36 at the output column 4. So that's how the move instruction, the bit shift left, and the add blocks work. You have to implement the tasks accordingly. using your knowledge and the knowledge that I have given you in these tasks, in these examples. I hope that this would be pretty much clear to you guys. Still, if you face any difficulty over here, you can mention them in comments, or you can ask that in the interactive session that we are going to have. So I hope that all of you would be in good health. Take good care of yourselves. Take care. Allah Hafiz.